We are going to see how the heavy minerals are used in stratigraphy. To do that, let's understand what is the meaning of heavy mineral. These are minerals with density more than that of quartz. What is the density of the quartz? The specific gravity is 2.65, and heavy mineral density can also be defined to be more than that of the feldspar. How much is the density of the feldspar? It varies from 2.54 to 2.76. Note that the value 2.65 lies between 2.54 to 2.76. Now, to be specific, heavy minerals usually have specific gravity more than 2.8 to 2.9. Note that these two numbers are both more than feldspar, more than that of quartz. How to do the heavy mineral studies? First of all, we have to collect the heavy minerals, and rarely more than 1% of sandstone from where they are extracted can give good amount of heavy minerals, which means voluminous rock samples such as sandstones to be collected and then the heavy minerals to be extracted. What are the heavy minerals? Here is a list: anatase, andalusite, apatite, cassiterite, chloritoid, chrome spinel, clinopyroxene, epidote group, garnet, kyanite, monazite, orthopyroxene, rutile, sillimanite, staurolite, titanite, tourmaline and zircon. These minerals all have got specific gravity, in fact more than 3. Note that the usual specific gravity requirement to call a mineral as heavy mineral has to be more than 2.8 to 2.9, and in fact within the list there are some minerals as heavy as specific gravity more than 4. Using these heavy minerals we can make high resolution correlation. I will explain soon, and such correlations are useful in the hydrocarbon reservoirs. Now, all the stratigraphic techniques have some words of caution. Here also, in case of heavy minerals, they have to be used carefully. The reason is weathering and other processes can alter the heavy minerals. Suppose a heavy mineral X is collected 2 in number, 2 grains, and then both of them are altered. Then should we count or should we ignore remains a question while studying the heavy minerals. The relative abundance of heavy minerals, and here the exceptions are garnet and tourmaline, can be made from the whole rock geochemistry. Suppose we have done a whole rock geochemistry, not just looking at specific heavy minerals, but all the minerals are taken care, then from there is a way to find out the relative abundance of the heavy minerals. But in this case, 2 heavy minerals will be excluded, which are garnet and tourmaline. Heavy mineral based stratigraphy can be made where no biostratigraphic information is present, or where such information exists and more fine scaled correlation is required. So, there are 2 possibilities: either there is no biostratigraphic information available, no fossil available. For example, you can find out some research paper that with the title heavy mineral stratigraphy for the barren strata. What is the meaning of barren? It means the strata is barren or devoid of fossils. So, this is one case where no biostratigraphic correlation can be done simply because fossils do not exist. In such a case, the heavy mineral stratigraphy can be useful, or consider a case where fossils are present and already a biostratigraphic correlation has been made and we want to make a finer correlation, then also heavy minerals can be used. What is the meaning of finer scale correlation is to be understood. Consider 2 lithological columns P and Q, and this is one unit of rock A, here is another unit of rock B, and here is a unit C, and here we have recorded A, B and C, and by biostratigraphy such a correlation has been established. Now, the meaning of finer resolution means this B is divided into portions such as B1, B2 and let us say B9, and here we make classifications small b1 dash, b2 dash and here small b9 dash. The meaning of finer resolution is that what was earlier broadly correlated capital B with small b, now B1 is correlated with small b dash 1 and B2 is correlated with small b dash 2, B9 is correlated with small b dash 9. So, we have explained the meaning of the fine scale correlation. Now, I am going to explain heavy mineral stratigraphy used from central Saudi Arabia, where the Carboniferous to Permian clastics were studied. To get into it, we have to understand a few indices involving heavy minerals. RZI means rutile zircon index, MZI means monazite zircon index, PZI means pink zircon and then total zircon index. Note in the previous to RZI, R and Z indicate rutile and zircon respectively, M and Z indicate monazite and zircon respectively. Here in PZI only one letter in capital Z, and that indicates zircon. Two varieties are there, pink zircon which is in the numerator and in the denominator total zircon which can be pink, which is pink zircon plus zircons of other colors. EZI, here E stands for euhedral zircon and divided by total zircon. ATI, here A stands for apatite and T stands for tourmaline. Now, all these ratios are multiplied by 100 and the minimum number of grains required to calculate RZI is 100. So, also PZI, EZI and ATI, whereas in case of MZI we need at least 200 grains to study. The application of these indices are there to find out the provenance, and in addition EZI and ATI are used to find out the environment. How come the provenance becomes important in the correlation can be understood. Consider this is a source of a heavy mineral H in two basins B1 and B2. It is assumed that the heavy mineral comes here and deposits at the same time. If that happens, then we can say that this sedimentary column were contemporaneous and we can join them, marking the correlation. But the question is, in case these heavy minerals deposits over the two basins were not contemporaneous, then the correlation will become diachronous, but in any case a correlation can be made. Now, coming to the study area of this central Saudi Arabia, this is the map and the red rectangle indicates the portion we are studying, that is Red Sea. Out of so many locations, let us focus on location 7, location 9 and location 12. In these locations, well data are available, well 7, well 9 and well 12. The line joining 7 and 9 and 12 are not exactly straight, but overall we can see from 9 towards 12 almost towards east and from 9 towards 7 is almost towards west. That is why here east and here west are written. Now, along with the geophysical data, the heavy minerals that have been found at different depths in well number 7, 9 and 12 have been plotted. Several units have been defined based on heavy minerals: unit UNZ0, UNZ1B, UNZ1A, UNZ1, UNZ2 and UNZ3. UNZ3 is the bottommost unit shown by this color, which can be seen here, and how the link has been made from well 7 to well 9 to well 12 has been shown. Now over it UNZ2, UNZ3 is over here. Unit UNZ2 is typical of ATI up to 65 and distinctly higher than UNZ3. In case of UNZ3, it has a low ATI and usually it is 0. What is ATI? It is the apatite tourmaline index given by 100 multiplied by apatite divided by apatite plus tourmaline. The number of apatite grains are written in the numerator and the total number of grains of apatite and tourmaline are kept over here. The minimum count of grains have been 100. UNZ2 given by this color can be seen over here, here and here, and in this way the correlation has been made. But a question exists, how good is the correlation? So a question mark is kept over there by the authors. The yellow color indicates UNZ1A, which is of low RZI, 0 ATI and extremely low EZI. EZI means the uvedral zircon total zircon index. ATI as told is the apatite tourmaline index, and RZI is the rutile zircon index. So basically these indices were calculated and then based on their low, 0 or high amounts they have been classified. Unit UNZ1B is given by this color and it is characterized by moderate to high RZI, ATI varying from 0 to 55 and it has got low to moderate EZI. Now in this way UNZ2 has been defined, UNZ1B has been defined, and it can be seen here the correlation. Within a single well the unit might get repeated. For example, here we are getting the yellow color and here also we are getting yellow color. So, there is a repetition. So, in this way a finer resolution has been achieved from a terrain in the central Saudi Arabia. Let us look at some other indices. The garnet zircon index, which is a percentage of garnet in garnet plus zircon, is represented by GZI. As usual, the second symbol Z and the first one together goes in the denominator. It is expressed in percentage. So, this ratio multiplied by 100 is expressed as GZI. All these indices are unitless. CZI is the chrome spinel zircon index. C stands for chrome spinel and Z stands for zircon, I stands for index. CZI is defined as percentage chrome spinel in total chrome spinel plus zircon. So, as I said earlier, heavy mineral assemblage primarily indicates the provenance. This is the most primary information that is coming, and from here we try to extrapolate the heavy mineral stratigraphy. There are some research papers that have used a combination of light and heavy minerals from sandstones for better provenance study. Minerals which are not heavy have been called as the light minerals. Talking more about provenance, it can be determined by focusing on specific pairs of minerals, not just random pairs of minerals. Minerals with similar shape, minerals with similar density, or minerals with resistance to erosion, and then we finally create the indices. For example, rutile zircon index useful in provenance studies and chrome spinel zircon index also useful in the provenance study. The sediment source can be differentiated, that single depositional site of rocks, depositional site, more than one sources of sediments can be worked out based on one or more mineral indices. For example, here is source 1 and here is source 2 and this is the place of deposition. Some deposition has happened. We pick up this material, extract the heavy minerals and comment on S1 and S2. If required, the heavy minerals can be further divided into two categories which are inherently resistant to weathering, that means in intact form we may find them not only resistant to weathering, also resistant to dissolution and transportation. Examples are zircon, monazite, tourmaline and rutile. And there are less resistant heavy minerals, typically olivine, pyroxene and amphibole. We know olivine in presence of water alters to serpentine and the process is known as serpentinization. Researchers have gone one step ahead. They are not just using the heavy minerals, but they are using synthetic heavy mineral assemblages. What does it mean? They are finding out the bulk geochemical data and then they are checking what heavy mineral assemblage can explain. Then it is known as the synthetic heavy mineral assemblage. From such an assemblage, the synthetic heavy mineral index can be worked out, and it has been shown that high resolution correlation can also be achieved based on such studies. I am going to discuss Oil and Natural Gas Corporation ONGC's work, which made a threefold classification of the shivalik based on the heavy minerals, and they divided the shivalik rocks into lower, middle and upper units. The study area belongs to the Indian Himalaya. First, to understand the general division of the Himalaya, this yellow unit represents the shivalik unit, the green unit represents the lesser Himalayan rocks, this color over there represents the greater Himalayan crystallines, and this blue color indicates the Tethyan Himalayan rocks. South of Shivalik Himalaya lies the Indo-Gangetic plain, and that is not a part of the Himalaya. The contact between the Indo-Gangetic plain and the Shivalik is the MFT. The contact between the Shivalik Himalaya and the lesser Himalaya is known as the MBT. The full form is main boundary thrust, and the contact between the lesser Himalaya and the greater Himalayan crystallines is known as the main central thrust. In short, MCT. The contact between the greater Himalayan crystallines and the Tethyan Himalaya has a name South Tibetan Detachment System. In the research paper dealing with the heavy mineral stratigraphy, I am going to focus on this Dehradun and southwest of it within this narrow region. A detail of this portion is shown in another author's map, where we find that the Shivalik rocks are folded into an anticlinal structure and is commonly known as, in this western part of the Himalaya, as the Mohand anticline. Now, the Shivalik rocks exposed in the Mohand area are poorly consolidated. Just to point out, this is Dehradun, and from here we are moving towards southwest direction. This deep green color and this faint green color represent the different units of Shivalik. So, we are studying in this portion. Also note that there are other studies of heavy mineral from the Shivalik sections in the Kashmir Himalaya. In the studied section, which means in this area, Mohand region, sillimanite is absent in the middle Shivalik. Now, by drilling in the Mohand area, lower Shivalik rocks have been encountered, and which consists of staurolite grains characterized by complete absence of kyanite. The lower Shivalik rock in this area is characterized by complete absence of kyanite grains. And the absence of sillimanite and kyanite are not due to intrastratal solution activities, which means we do not see residual kyanite or residual sillimanite, or the sillimanite and kyanite grains that, or the sillimanite or kyanite grains with boundaries corroded. No, we do not see such things. Now I come to the research paper. Sinha 1970 has correlated the different sections in the Mohand area based on heavy minerals. Sinha classified Shivalik into three parts, lower, middle and upper, or put in another way, Sinha provided heavy mineral information for the lower Shivalik, middle Shivalik and the upper Shivalik. In lower Shivalik he found staurolite is present there and there is a complete absence of kyanite. This lower Shivalik I was referring in the previous slide here, that by drilling lower Shivalik was found from the Mohand region. The middle Shivalik has been divided into two parts, A and B. A consists of garnet, tourmaline, staurolite and kyanite. So, kyanite is found in the middle Shivalik, and one distinction between the lower Shivalik and middle Shivalik is that while in the lower Shivalik kyanite is absent, in middle Shivalik kyanite is typically present. Now we go to the upper unit of the middle Shivalik, that is unit B. Here we get hornblende and the lower Shivalik assemblage. That means this assemblage comes back over there. Now I come to the upper Shivalik region and it is divided into C, D and E. In the upper Shivalik, in the Mohand area, we find the bottommost unit is the unit C, which consists of sillimanite, and unit B is assemblage, which means hornblende and then staurolite and then complete absence of kyanite. In unit D, which is the intermediate unit between C and E, is characterized by flooding of ore minerals. That means too many ore minerals are found, but note that the unit D in upper Shivalik in the Mohand area is economically not important. It is economically not feasible to extract these ore minerals. It also has got very low amount of garnet and very rare kyanite. So, kyanite got again reduced in number. There are rounded zircons and tourmaline grains. The topmost unit of upper Shivalik is E, unit E, which is characterized by very low garnet, which is same as unit D, rare but persistent sillimanite, important, and abundant kyanite. One finds that from unit D to unit E, the kyanite proportion increased significantly. In this figure, this portion is a southwestern limb of the Mohand anticline, where it is. This is the Mohand anticline. By saying southwestern limb, we mean this portion. Several cross sections were studied and those are named here, and the stratigraphic column has been provided. And in this portion of the figure is the northeastern limb of the Mohand anticline. This is the northeastern limb of the Mohand anticline. And in this place also, Sinha studied several lithostratigraphic sections, and then in both the limbs of the Mohand anticline, he defined unit A, unit B, then in upper Shivalik C, D and E, and here unit A in middle Shivalik, unit B and then C, D and E. In this diagram, the lower Shivalik has not been presented, it has been encountered only by drilling, and so what has been presented in this diagram are the different sections which are available by doing field work. This diagram does not present the lower Shivalik. So, we can say this diagram based on field studies. While talking about the layered sediments, verbs are of special importance. Original definition of verb is that there are at least two layers or laminae, that means close spaced bedding planes, and they are characterized by different compositions, textures and structures. They can be annual layers of fresh sediments. Say every year fresh sediments are deposited. So, each layer marks 1 year. The verb database has been available. These verbs can extend for 200 to 500 meter and the record can be for 1000 to 2000 years. Radiocarbon dating is applied here. In the present literature, verb and annually laminated sediments are synonymous. They have the same meaning. The types of verbs, they can be clastic material, there can be biogenic material, there can be endogenic material, and mixed type is also possible. That means there can be a verb which is a mixture of, where the sediments are a mixture of clastic and biogenic materials. Past climate can be worked out based on the verb studies. Marine verbs also exist. It is not that all the verbs are non-marine, there can be marine verbs, and such verbs can develop at around 2 km of water depth. When we use the word verbite, in the glacial lakes, couplet of coarser material bearing light colored and finer material bearing dark colored represents summer and winter deposits respectively. This means, and is important for the students to remember, coarser materials and they are light colored were deposited in summer, and in the coming winter fine material bearing dark bands get deposited. There can be drop stones here and there. These are the large sediment particles that get deposited and disturb the verbite layers. So, just to make a cartoon out of this statement, there can be couplet of coarser materials, there can be light colored coarser materials deposited during the summer, and during the winter when the top layer of water is frozen, water movement is restricted. So, the fine particles along with the organic materials get deposited, so that is dark color. This together will indicate 1 year. I am going to show you alternating light and dark colored materials, and one can make out most probably that is indicating summer followed by winter deposit. So, one can actually count, if you are very sure summer and winter variation is demonstrated by some other studies, how many summers, how many winters and how many years are indicated by such a succession. This is how the verb deposits can look like. They are usually layered. The layering can be sharp, almost never perfect straight lines. In some cases, there is a gradational contact between the black layer and the white layer. These black layers can vary in thickness. The boundary need not be a straight line. In another case, we can find much curvature, much curved boundaries between the black and the white layers. So, also in the right hand bottom image, this is a global distribution of the verb records, but note that there can be also other plots on the globe. At least as per Ojala et al. 2012, very few verb records are there in the Asia. Most of the records he is finding, he is documenting from the Scandinavian countries and further west scattered examples. What is a rhythmite? These are the layers showing a repeated pattern of deposition. So, there is some similarity between the definition of rhythmite and verb. Verb is a kind of rhythmite. The rhythmite can form in glacial or in marine environment. Astronomically induced tidal periods might be the governing factors. Researchers might be able to comment on the astronomically induced tidal periods by studying the rhythmites. And there are some research papers dealing with the study of the stratified layers of sediments and commenting about Earth's past rotation history. An Indian example of rhythmite is the Chaibasa formation in eastern India. Also, it has been documented from Ghatshila from eastern India. Let us focus on the Chaibasa sandstone, which is of Proterozoic age. Where it is located is to be understood. This is the India map, and the Tata city is here, plotted over here. Now, the different rock types have been plotted in the map, has been shown in the map. This is the Chaibasa formation, and here we find alternate layers, that means rhythmites, and this is how it appears.